Let's look at how to calculate the arc length of a curve. There's various cases where you can do this, but the most basic is where the curve is the graph of y equals f of x, some function of one variable. And the idea with any integral is divide and conquer. The whole is the sum of its parts. The length is going to be the integral of a bunch of little bits of length. And for various reasons, we don't use L for the little bits. We use ds as the notation for a tiny little bit of length. And I'm going to do this in a very quick and dirty way that the book does a more careful way, as usual. But we're going to think of this as a tiny little bit of the curve. And so we're segmenting the curve into tiny little bits of length, and we're just going to add those up. Well, how are we actually describing the curve? Remember, it was a function of x, and so x is going to be going from a to b, and so we can use to figure out all the little bits of the curve, we're going to say this little bit of the curve here, I'm going to blow this up, is going to be everything where x goes from a certain x value to the next x value, and that the lapse in x that we're going to allow is dx. As usual, we're going to call how much y changes dy, but remember that as soon as we do that, we're doing an approximation. We're not really taking this real curve. We're taking and approximating that by a straight line, and so that's going to be like the tangent line. So as usual, if this were a finite length, we're going to get just an approximation. To say dx and dy, to suggest these are infinitesimal quantities, we're thinking about really taking the limit. But let's just see what happens if we would use this straight line approximation, and this were really a real quantity dx and a real quantity dy, then we just get Pythagoras. I'll try not to write it diagonally because that probably won't come out well. So dx squared plus dy squared. That really should be dx sort of quantity squared plus dy quantity squared, but you often drop the parentheses knowing that dx is just one thing. It's not the quantity d times the quantity x and the x only squared. And so that's going to be ds. And that's really all there is to it, is the whole is the sum of its parts. Each part here is calculated by dx and dy. That's really the fundamental thing. And then the question is, how do we get that as an ordinary integral in terms of x, say? And that's not too hard, because if dx is the variable, if x is the variable I'm going to use here, I know what dy is in terms of dx because I know the slope. Dy dx is just f prime. We know that dy dx equals f prime of x. And so dy is just f prime of x dx. Good old differentials. Okay, so the differential notation is almost always the thing that you really end up reaching for when you're doing integrals. Okay, so let's just put that together. I think I'll erase that little inset picture. And so we're just going to substitute that in. And so we're going to get the integral as x goes from a to b of the square root of dx. I'll go ahead and put things in parentheses to be careful, at least during the derivation, plus f prime of x dx squared. Okay, so I've used that. And now I get a common factor of dx squared inside a square root. So this guy, 1 plus that squared dx. What happens here, this is very, very symmetrical. This is a very nice way to remember it. And this actually lets you set it up as an integral in the y variable if like x is a function of y. We saw that with like areas between curves and volumes, that sometimes you want the y to actually be the variable. So this turns into an integral perfectly nice in terms of the y variable. And I'll let you look in the book for those examples. And here I broke the symmetry by saying, well, you know, I gave it to myself as y equals f of x. X looks like it wants to be the variable of integration. And so I get this somewhat asymmetrical formula coming out because I broke the symmetry and I biased in terms of x. So this is still ds. And what you can also think about it is this is a stretch factor. If dx is a certain length here, the steeper this curve is, the bigger f prime is, the more actual arc length on the curve is going to be represented by dx. There's sort of one metaphor is like you put the sun up here, and you can actually have a fairly long little stick here with a fairly short shadow if it's steep and the sun is up here overhead at noon. So this is a stretching factor. That's another way to say it. So there's our formula for arc length in the simplest case where y is f of x. And again, this is a really nice way to remember a very general idea, and that generalizes best to other cases. Let me just do 2 examples, try to run through them fairly quickly, but I think I'll include them all in this one video. I'll go ahead and go to workplace at this point. So let's say f of x equals sine x. Then f prime, of course, is cosine. I guess I'll put that in, but we kind of know that pretty well. And here's the graph. And for any arc length problem, if you are looking at a graph of it, you get some idea of the length. So for example, a straight line from 0, 0 to pi over 2 comma 1, you'd just do the actual Pythagoras, not with these infinitesimal differentials and everything. And you'd multiply by 2, you get about 3.724. So it does go through those 3 points, and it's curvy a little bit, so it should be bigger than that kind of broken straight line estimate. And you just put this in, very simple example. Remember, it's the derivative, and then you square it, and then you add 1, and you square root. You should think of the square root and the addition and the squares as from Pythagoras, but of course it's you have to do that derivative inside first. So it's a little interesting. You're mixing a derivative and an integral, but that's what the geometry told us. We're going to integrate that from 0 to pi, and indeed we get something just a little bit more than 3.7. So that's pretty straightforward. But let me tell you though, I wanted to do an example here. Notice I didn't show you how to do this integral. That's because nobody can do this integral analytically. It is something you have to do numerically. And realistically, with most arc length integrals, because you're putting this fairly arbitrary function into a square root, it has to be really contrived for it to actually work out nicely. I will show you one of those because there's one kind of pattern that comes in terms of contriving these that's really pretty and is something to be familiar with, especially if a book wants to get you to do this all analytically, or if like the AP or something. So here's one. I did pull this out of Stewart, modified just slightly. The log of 1 minus x squared, and we're going to go from x equals 0 to x equals a quarter. Turns out it just goes from 0, 0, and then goes sort of gently down. It's not super curvy, so it's not that much more than a straight line from 0 to 1/4 minus 1/20th-ish. And honestly, it's not going to be much more than this straight line 0 to a quarter. So again, we have some idea, should be a bit bigger than a quarter. So f prime, we get 1 over 1 minus x squared, but then times a chain rule, we get minus 2x on the top. And then we get, we're going to put that in, we're going to square it, put it into 1 plus the square root, and then how is that going to work out? Okay, so let's look at this. Here's the whole thing written out. We've taken the square of that derivative, 1 plus square root, and then I put it over a common denominator, and I'll tell you, and I purposely was going to leave a space here. Okay, how does this work out nicely? It turns out to work out very, very nicely. But let me just do it on the fly here. And we're going to get 1 minus x squared squared. So I'm going to write that all out. 1 minus 2x squared plus x to the 4th. And then, of course, all over that denominator. And if I could actually get the cursor where I want it to go. Okay, and look what happens. This is very interesting. This was a binomial, an a squared minus 2ab plus b squared. It turns out that I'm adding exactly enough over here for x squared to turn that into 1 plus 2x squared plus x to the 4th over the same denominator. But wait, that is another perfect square trinomial, but the square of 1 plus x squared. And now I've got a perfect square in the inside. Both the numerator and the denominator are perfect squares, so it just cancels out. Oh, wait, it's really the absolute value, but notice that these are all positive quantities. So watch out for that. That can be tricky. The square root of a square of something is the absolute value, but here they happen to be positive. A little bit of partial fractions that I'm not going to show. Fairly easy little partial fractions. Gets you into actually a really nice integral, but yeah, you have to do a little bit of partial fractions. Then it becomes this guy, and then a log. So the point of the video is not go through this calculation, but certainly pause and think about if you want to do any of these steps. And guess what? We get something that's just a little bit bigger than 1/4. And that's it.